Assalamualaikum. My name is Alishba Sajjad and I am from the Department of BS Biochemistry. My roll number is 001. Today I am here to present three topics from gas chromatography. Here are some of the methods: carrier gas selection and flow rates, by stationary compound selection and by inlet types and flow rates, and by sample size and injection technique and through sample injection. So what is method? Basically, the method is the collection of conditions in which the gas chromatography operates for a given analysis. Method development is the process of determining what conditions are adequate and are ideal for the analysis required. Conditions which can be varied to accommodate a required analysis include inlet temperature, detector temperature, column temperature, and temperature program, carrier gas and carrier gas flow rates, the column stationary phase diameter in length, inlet type, and flow rates, the sample size, and injection technique. Depending on the detectors, there may be a number of detector conditions that can also be varied. Some GCs also include valves which can change the route of sample and carrier flow. The timing of the opening and closing of these valves can be important to method development. So here it comes some explanation of these methods. First is carrier gas selection and flow rates. Basically, it is a typical carrier gases, which included like helium, nitrogen, argon, hydrogen, and air. Which gas to use is usually determined by the detector being used. For example, like DID requires helium to as a carrier gas when analyzing gas samples. However, the carrier is sometimes selected based on the sample's matrix. The gas linear um, the carrier gas linear velocity affects the carrier gas linear velocity affects the analysis in the same way that temperature does. The higher the linear velocity, the faster the analysis, but the lower the separation between the analytes. For example, when analyzing a mixture in argon, an argon carrier is preferred because the argon in the sample does not show up on the chromatogram. Safety and availability can also influence carrier selection. For example, hydrogen is flammable and high purity helium can be difficult to obtain in some areas. As a result of helium becoming more scarce, hydrogen is often being substituted for helium as a carrier gas in several applications. Um, like the purity of carrier gas is also frequently determined by the detector through the level of sensitivity needed can also play a significant role. Typically, purities of 99.995% or higher are used. The most common purity grades required by modern instruments for the majority of sensitivities are 5.0 grades or 99.999%. Pure meaning that there is a total of 10 ppm of impurities in carrier gas that could affect the result. The highest purity grades in common use are 6.0 grades, but the need for detection at very low levels in some forensic and environmental applications has driven the need. Um, Selecting the linear velocity is, therefore, the same compromise between the level of separation and length of analysis as selecting the column temperature. The linear velocity will be implemented by means of the carrier gas flow rate with regards to the inner diameter of the column. So there are many GCs, modern GCs, however, electronically measure the flow rate, and electronically control the carrier gas pressure to set the flow rate. Consequently, carrier pressures and flow rates can be adjusted during the sun, creating pressure flow programs similar to temperature programs. Let's move on to the next method, which is stationary. Next, move on to the next method, which is stationary compound selection. Um, in this method, polarity of the solute is crucial for the choice of stationary compound, which is an optimal case would have a similar polarity as the solute. Common stationary phases in open tubular columns are cyanopropyl dimethyl polysilohexane, carbox, polyethylglycol are used because for packed columns more options are available. And the next method is inlet types and flow rates. The choice of inlet type and injection technique depends if the sample is in liquid, if the sample is in liquid gas, absorbed or solid form, and on whether a solvent matrix is present that has to be vaporized. That means like dissolved samples can be introduced directly onto the column via a injector if the conditions are well known. If a solvent matrix has to be vaporized and partially removed, a injector is used. Gaseous samples like air cylinders are usually injected using a gas switching value system. Adsorbed samples are adsorbent tubes or introduced using either an external on-line or off-line absorption apparatus such as a purge and trap system or are dissolved in the injector. Move on to the next one, which is carrier gas selection and flow rates. Carrier gas selection and flow rates. Typically, carrier gas includes next move on to the sample injection. Let's move on to the sample injection. The real chromatographic analysis starts with the introduction of the sample onto the column. The development of capillary gas chromatography resulted in many practical problems with the injection technique. The technique of column injection, often used with packed columns, is usually not possible with capillary columns. Some general requirements which a good injection technique should fulfill are that it should be possible to obtain the column's optimum separation efficiency. It should allow accurate and reproducible injections of small amounts of representative samples. It should induce no change in sample composition. It should not exhibit discrimination based on differences in boiling point, polarity, concentration, or thermal catalytic stability. And it should be applicable for trace analysis as well as for undulated samples. This is a diagram of sample injection, which is like maybe it's a capillary through which the process takes place. Next one is column temperature and temperature program. Column temperature and column program, a method which holds the column at the same temperature for the entire analysis, is called isothermal. Most methods, however, increase the column temperature during the analysis. The initial temperature, the rate of temperature increases, and final temperature are called the temperature program. A temperature program allows analytes that elute early in the analysis to separate adequately while shortening the time it takes for late eluting analytes to pass through the column. The choice of column depends on the sample basically and the active measured. The main chemical attribute regarded when choosing a column is the polarity of the mixture, but functional groups can play an important role in column selection. The polarity of the sample must closely match the polarity of the column stationary phase to increase resolution and separation while reducing runtime. The separation and runtime also depends on the film thickness of the stationary phase, the column diameter, and the column length. Now move on to the next point, which is data reduction and analysis. Data reduction and analysis. Generally speaking, if a sample is already in gas form, it's introduced and volatilized in the injection part of the gas chromatograph. The gases then pass through a column which is coated with material to attract the various components of the sample at varying degrees. This is called the stationary phase, and it's the level of attraction during this phase that causes components to separate and elute at different times, which shows as peaks on the resulting chromatogram. Basically, there are two there are two like axis, the x-axis called retention time and the y-axis called concentration or intensity counts. The x-axis and y-axis in combined form called qualitative analysis. Generally, chromatographic data is presented as a graph of detector response. Y-axis against retention time and x-axis, which is called a chromatogram. This provides a spectrum of peaks for a sample, representing the analytes present in a sample eluting from the column at different times. Retention time can be used to identify analytes if the method conditions are constant. Also, a pattern of peaks will be constant for a sample. Under constant conditions and can be identified complex mixtures of analytes. However, in most modern applications, the gas chromatograph is connected to a mass spectrometer or similar detector that is capable of identifying the analytes represented by the peaks. And there is also another analysis called quantitative analysis, in which area under a peak is proportional to the amount of analyte present in the chromatogram. By calculating the area of the peak using the mathematical function of integration, concentration of an analyte in the original sample can be determined. Concentration can be calculated using a calibration curve created by finding the response for a series of concentrations of analyte or by determining the relative response factor of an analyte. The relative response factor is the expected ratio of an analyte to an internal standard or external standard and is calculated by finding the response of a known amount of analyte and a constant amount of internal standard, a chemical added to the sample at a constant concentration with a distinct retention time to the analyte. Here is one of the examples. The x-axis retention time, as you know, I have told previously that the gas chromatogram shows the amount of time taken for the analytes to pass through the column and reach the mass spectrometer detector. On the other hand, the y-axis is concentration is basically related to the concentration or intensity counts, which is typically um, typically the y-axis or the area of peak is a reflection of the amount of specific analyte that's present. The next one is the example. Sorry, this is what is the difference in gas chromatogram models at higher level depending on the type of sample and the desired outcome. Gas chromatography analysis can use several different means of sample introduction such as static headspace, analysis, thermal dispersion, and direct injection, as well as different types of detectors such as flame ionization, electron capture, and of course mass spectrometry. But one key point we did like to reiterate is that it's important to remember that the systems and parameters used for an analysis need to be similar when comparing results from two or more different analyses. Here is the example. Here is the graph. Um, this basically it is vegetable oil analysis. As you can see in this case, food manufacturer was considering switching to a new vegetable cooking oil. After a vegetable oil analysis of both their current and a potentially new oil, we found that their current oil contains several different compounds, including palmitic acid, retention time of 19.00 minutes. 9.00 minutes, linoleic acid retention time of 20.6 minutes. As you can see that oleic acid retention time of 20.7 minutes. This one is the and stearic acid retention time of 20.09 minutes. The next one is application. This one is application food analysis. The food industry basically relies on the technique of gas chromatography for several applications, including the quantitative and qualitative analysis of food, the analysis of food additives, components of flavor and aroma, and the detection and analysis of contaminants such as environmental pollutants, pesticides, fumigants, and naturally occurring toxins. Basically, gas chromatography is vital to the food industry for ensuring the safety of food products, preventing the products from becoming available for consumption. The technique is also essential to ensure the quality of food products, ensure the flavor, texture, and smell, etc., while other techniques are implemented by the food industry. Gas chromatography remains a highly favored method due to its ease of use and cost effectiveness. Next point is quality control. Manufacturers rely on gas chromatography for quality control. Companies that produce cars, chemicals, and pharmaceuticals in particular are big adopters of the technology. The pharmaceutical industry uses gas chromatography to help produce pure products in large quantities. The method is used to ensure the purity of the produced material, eliminating inconsistencies in pharmaceutical products. Currently, there is also a growing use of this method within the pharmaceutical industry to separate chiral compounds. Studies have shown that the interiors of new automobiles release a significant amount of volatile organic compounds. For this reason, gas chromatography has been adopted by the automotive industry to identify. For this reason, gas chromatography has been adopted by the automotive industry to identify and measure the chemicals that are released into the air inside the car from its carpets, door links, seat covers, and other interior materials. Scientists aim to reduce the level of harmful toxins released into the interiors of new vehicles. Producers of chemicals also heavily rely on gas chromatography, particularly when making emulsifiers, solvents, and co-solvents to ensure that they maintain the same quality when production is scaled up. Next one is research. Gas chromatography is fundamental to many research areas, in particular for the analysis of meteorites and natural products. Scientists use gas chromatography to analyze the composition of meteorites that fall to the Earth. Gas chromatography is fundamental to many research areas, in particular for the analysis of meteorites and natural products. Scientists use gas chromatography to analyze the composition of meteorites that fall to the Earth. This provides vitally important information regarding the nature of life outside of Earth as well as revealing details about primitive life on Earth. Specifically, many studies have been conducted with gas chromatography to determine the presence of rivals in meteoroids, the building block of our DNA. The next one is blood alcohol analysis. Basically, by using gas chromatography, scientists have to detect blood alcohol levels. It has been used in 1950. Since then, it has continued to be used to detect how much alcohol a person has consumed to help gauge how impaired their normal functioning may be. Also, it has been adopted by forensic scientists to determine blood alcohol levels at the time of the death. In forensics, for many years, gas chromatography has been used in forensic science. Mostly, it is used to determine the circumstances of a person's death, such as whether they ingested poison or consumed drugs or alcohol in the few hours prior. Scientists take samples of blood and fibers from the crime scene and analyze them using gas chromatography to help investigators piece together the facts. In the same way, measuring air pollution, gas chromatography is being used to combat the problem by monitoring the levels of harmful pollutants in the air so that scientists can visualize where air pollution is more concentrated and how this changes throughout the day and the year to develop effective preventative methods. The overall summary of these applications is that there are a wide number of applications of gas chromatography. Its benefits such as its high sensitivity and relatively cheap operating cost has made it appealing to many industries needed to detect and measure compounds and molecules within a sample. The method will likely continue to be a key technique used across all over the sectors. So there is a vast variety range of applications of gas chromatography present in the world. Is that all from my side? Thank you.